So also from my side, welcome to this presentation. Next month it will be on the quaternary. This month we'll go a little bit deeper in geological time. And the title of my presentation today will be Pre-Cenozoic Cyclostratigraphy and Paleoclimate Response to Astronomical Forcing. And I'm gonna start right away with giving the main message from my presentation, which will be that in order to apply cyclostratigraphy in a successful way to build pre-Cenozoic timescales, it is important to harmonize cyclostratigraphy between different continents, between long distances. And in this case, in my presentation, I will show the work that has been done primarily in Münster in my working group to harmonize late Devonian cyclostratigraphies between Europe and North America. And the reason why that is important, I already told you, is to build geological timescales and to build improving geological timescales with higher accuracy and higher precision, of course. And this is a topic I started to be interested in during my PhD in 2014. And back in the days, I approached this problem primarily from a statistical point of view. And you see it also in the title here on the left top here. I approached this using Bayesian statistics. And this approach was then also integrated in GTS 2020 and got a follow-up paper in 2021 by Claire O'Harrigan, all very focused on statistics. But over the last couple of years, I started to realize that in order to improve these geological timescales, of course, statistics is important, but the reproducibility of cyclostratigraphic results is even more important. And I want to read to you like two sentences my colleagues and I rewrote in a reviews paper that came out earlier this month. And there we write, multiple independent astrochronologies must be constructed for the same interval in time before a consensus can emerge. And to date, the cyclostratigraphic community is well underway to reach such a consensus for the late Cretaceous and a substantial portion of the Mesozoic. And progress has been made in the late Devonian. But of course, further work is required to reach a consensus. And for that reason, we promote in the review paper, Paleozoic cyclostratigraphy as the next frontier in cyclostratigraphy. So that's a little bit the background for my presentation today. And other very important concept that I want to introduce now at the start of my presentation is the concept of the astrochronozone. It is the essential building stone for a cyclostratigrapher, and you can compare it a little bit with a biozone for a biostratigrapher or a magnetochron for a magnetostratigrapher. So what is an astrochron? Basically, astrochronozones are 405,000 year eccentricity cycles that we count back from the present into the geological past. And if you now focus here on the left-hand side of the figure, you're looking at the Cenozoic-Mesozoic boundary, so the Cretaceous-Paleogene boundary, and you're looking at a cyclostratigraphy for the latest Maastrichtian constructed by Sietske-Batenburg, and you see the three latest 405,000 year eccentricity cycles of the Maastrichtian. And everyone agrees by now that they should be tuned, they should correlate by these three cycles in time. These are different astronomical solutions, the different Zeebi and Laskar solutions for eccentricity. And if you count back those cycles from the present into the past, these are astrochronozones 164, 165, and 166. And everyone agrees that the Cretaceous-Paleogene boundary occurs in astrochronozone 164. Now we play the same game for the Paleozoic-Mesozoic boundary. So we go back in time 251 million years, and here is the Meishan GSSP section. Same story here. The three 405,000 year cycles extracted from the geological record. And here you see the problem. If we go that far back in time, the different astronomical solutions provided to us by astronomers, they completely get out of phase. They get chaotic, or they show disagreement on the phase relationship. And so you can't, at this point, at the state of the art of cyclostratigraphy, we can't say, everyone agrees that this is the 405,000 year cycle that spans the Paleozoic Mesozoic boundary. Here is the Permo-Triassic boundary, but no one can say whether the Permo-Triassic boundary occurs in astrochronozone 623 or astrochronozone 624. So that is why it is important to invest time into pre-Cenozoic cyclostratigraphy, because that's one of the goals for the next 5 to 10 years, to determine whether we have 623 or 624 astrochronozones in the Cenozoic and Mesozoic combined. But today I want to go even further back in the geological history of our planet, to the Devonian, and more specifically to the warm house of the late Devonian. And I structured my talk in 3 intervals, where I will focus on harmonizing cyclostratigraphies between Europe and North America in order to come to such a consensus that we can use these astrochronozones as the timekeeper, as the geological timekeeper in the even in the Paleozoic. So I'll start with the Kellwasser interval, the Fresnel-Furmanian boundary. I'll make a little detour about millennial scale climate cycles, and then I will go a little bit younger, higher up in the stratigraphic column towards the Furmanian. But as I promised, we'll start with the Kellwasser interval, and I'll bring you to a section that maybe many of you know from mapping courses or field courses that you might be teaching. These are the Adolf-Bender-Schiefer in a section close to Adolf, actually, and we call this section the Winsenberg road cut. It's a section that my PhD student, my former PhD student, Nina Wichern, who you see here on the picture, studied. And you see here, the section starts with the Uslan, massive limestone. Here we have the lower Kellwasser black shales. The upper Kellwasser black shales are here around the corner, and in between the lower Kellwasser and the upper Kellwasser, we have the intra-Kellwasser cyclic shales. And here you see a picture from around the corner. So now you see here the upper Kellwasser black shales, and it continues with more cycles, more lithological cycles in the lower Furmanian, shales. And Nina took about 500 samples from that road cut at centimeter scale resolution. She powdered them and she measured them with an XRF gun. And based on the XRF results, we were able to estimate calcium carbonate content. And you see this cyclical pattern between more shaly layers and more limestone-rich layers. And based on the time series analysis of this blue line, this blue record, she interprets this cyclicity that occurs on a decimeter scale as precession driven. Why is that? Well, I'll show you a little zoom in to demonstrate that. So we're zooming in now here at this interval just above the lower Kellwasser black shales. You still see here some darker shale at the bottom of the picture. And then you see 1, 2, 3, 4 very well pronounced limestone layers that are also here in the blue data, of course, very well expressed as very clear limestone shale cycles. And you see that you see that the cyclicity with the letter P has been interpreted as precession cycles based on biostratigraphic constraints that we have. And you also see that these cycles are very well expressed here in the upper part of the picture, not so much in the lower part of the picture. And that is reminiscent of cyclostratigraphy Patterns that are well established since the 90s from the Mediterranean realm, cycles and bundles that we can observe in the Neogene from the Mediterranean. Here, you're looking at a picture from Fritz Hilgen, and you see basically the same pattern: intervals where precession cycles are very well expressed, and those are eccentricity maxima, and intervals where we do not see those very well expressed precession cycles. Those are the eccentricity minima. Why do we have these cycles and bundles? That is because eccentricity is amplitude modulating the precession cycle. So during eccentricity maxima, precession cycles can be at full force. They can force the climate system with a high amplitude, and therefore they're very well expressed in our lithological record. During eccentricity minima, for example, the amplitude is much, much reduced, and therefore the impact on climate is much reduced, and the lithological expression is also much reduced. That's why we have eccentricity minima so well pronounced or so visible in the lithological record. So back to the picture we've seen earlier, Nina interpreted this interval as a 100,000 year eccentricity maximum, and the lower portion of the slide as an eccentricity minimum. I can basically play this game showing you pictures throughout the entire lithological column. Now I want to show you that this pattern continues into the Furmanian. So the Franian-Furmanian boundary is situated here, close to bed number 47. And we see here again the interpretation, the astronomical interpretation by Nina Wichern with the P cycles indicating individual precession cycles. And you see here a bundle of 3 precession cycles closely spaced on this decimeter scale, a interval with low, where these shales are absent, basically, and then the shales come back here in the top. So also here, the same game, where precession cycles are very well expressed. This is interpreted as a 100,000 year eccentricity maximum, an eccentricity minimum, followed again with a 100,000 year eccentricity maximum. So this is the kind of game a cyclostratigrapher plays throughout a rhythmic section like that. And so I showed you the example here from just above the lower Kellwasser in my first slides, and then from the earliest or the lowest Furmanian here in this dashed rectangle. And of course, Nina did that for the entire section. And when she did that, she comes to a time estimate of 900,000 years between the onset of the lower Kellwasser, so the base of the lower Kellwasser, and the base of the upper Kellwasser dark shales. Keep in mind that number of 900,000 years between the lower and upper Kellwasser onsets, because now we will move from Germany to the United States. Right? We want to harmonize cyclostratigraphies between Europe and North America. So now I bring you to the Catskill Delta, to New York State, where the Kellwasser interval looks like this. Again, quite rhythmic interpretation. And in this case, the cyclostratigraphic interpretation was done by a master student, Jana Klisevic, also from Münster. She basically adopted a very similar approach. She also used, she sampled the section, and she measured with the portable XRF in the lab. So it's portable XRF, but applied in the lab. She measured at centimeter scale resolution the properties, the geochemical properties of those samples, and she selected titanium over aluminium as the proxy to make her astronomical interpretation. And you can see here from the slide, these red cycles that she extracted here, that's her interpretation of the precession cycles with a period around 20,000 years. Here on the picture, I try to follow where she puts the 100,000 year bundling. And then here, the purple line shows the 400,000 year cycles. Here for New York State, I will not go into all the details of why she came to this interpretation, but I want to highlight that if you measure time between the onset of the lower Kellwasser here and the onset of the upper Kalwasser, which occurs here in the section, you come to a duration of 880,000 years. So a result that is in quite good agreement with the time estimate provided by Nina Wichern for the interval between the onset of the lower Kalwasser and the onset of the upper Kalwasser. So both Kalwasser events are characterized by a positive carbon isotope excursion. Nina estimates 900, Jana estimates 880,000 years for that interval. And if you go look in the literature, you get, of course, a wide palette, a wide portfolio of different age estimates based on cyclostratigraphy. I'll start with my work. In my PhD, I came up with 600,000 to 700,000 years for that interval. Mike Whalen, 500,000 years. A study from Louisiana, if I remember correctly, 450,000 years. And Christine da Silva, 670,000 years. And for southern China, there is a very long estimate of 1.3 million years. And what I want to highlight here is that despite there is quite some difference between 450,000 years and 900,000 years, all the estimates in blue agree on the scale of the astrochronozone. Believe it or not, but all authors between Lu, Whalen, the Vleeschouwer, da Silva, Klisewicz, and Wichern, they all agree that the lower Kalwasser occurs in its own 405,000 year astrochronozone, then that there is one astrochronozone in between the two Kalwassers, and the upper Kalwasser occurs in its own astrochronozone. In my papers, you will see that I count them astrochronozone 15, 16, 17. So this is the 15th astrochronozone in the Franian, the 16th and the 17th. That's why these numbers are here. So all the authors in blue, they agree on the fact that there is one 405,000 year astrochronozone between the lower and the upper Kalwasser event. Only Ma et al. From China, they suggest that there are two astrochronozones in between the lower Kalwasser and the upper Kalwasser. So that is the kind of consensus we need to obtain in order to use these kind of cyclostratigraphic estimates to inform the geological timescale and to improve the geological timescale. So I think very fundamental work on different sides of the Atlantic Ocean. Of course, both Nina and Jana in New York and in Winsenberg, they sampled at centimeter scale resolution. So it's very tempting to increase the resolution of cyclostratigraphic correlation beyond the 405,000 year astrochronozone. And I highlight here that this variability in New York in sulfur looks quite similar to the variability we have in Winsenberg in calcium carbonate content. But for now, we're going to refrain from making higher resolution correlations, cyclostratigraphic correlations between the US and Germany, where for now we're going to keep our cyclostratigraphic correlation to the scale of the three astrochronozones, astrochronozone 15, 16, and 17 in the US, 15, 16, and 17 in Germany. Nevertheless, these very high resolution rhythmites, sometimes millimeter scale, centimeter scale rhythmites that you observe all around the world, especially in the Franian, are quite intriguing. And there is such centimeter scale variability both in Germany and the US just prior to the lower Kalwasser event. In the first picture I've shown you, I said that the Winsenberg section in close to Adorf starts with the Usselen limestone. So the Usselen limestone is a massive limestone bed that is considered the lower Kalwasser prelude. So the lower Kalwasser everywhere sits directly on, well, in Sauerland, in the Sauerland of and in the Kellerwald. the Ussulan limestone immediately sits below the lower Kalwasser dark shales, and it looks like this at different localities. You see these centimeter scale variabilities in clay content, basically. And so what Nina did, here you see Nina on the video, she measured pieces of the Uslan limestone. So you see here, we sampled the Uslan limestone continuously, and we measured that with micro XRF to look at the rhythmites that characterize these the Uslan limestone, and we looked at the potential of correlating individual layers between Winsenberg, Afeld, and Steinbruch-Schmidt. And Nina actually managed to establish such a correlation, even though it has its uncertainties. But the most likely correlation implies that the Uslan limestone itself has a diachronous base between the different localities, but an isochronous top. So the top of the Uslan limestone seems to be isochronous. So the onset of the Kalwasser seems to be simultaneously occurring across the basin where the Uslan limestone crops out. Interestingly enough, if we go back to New York State, if we go back to the Catskill Delta and we look immediately below the lower Kalwasser, so here we have the Pipe Creek Formation, which is the equivalent of the lower Kalwasser. Below that, we have the Angola Formation, and the Angola Formation would then be the Uslan equivalent. And the Angola Formation is also rhythmically banded, as you can see here from the drill core that we obtained from the Angola Formation. So during field work, we got to know this guy here in the center part of the slide. This is Randy, and Randy for us drilled a 9-meter core into the Angola Formation, and he made a very nice Instagram story out of that. And a new PhD student in my group, Jakob Kwabek, did the same approach with the micro XRF scanner to measure this 9-meter core at micrometer, or at, I have to say, 0.5 millimeter resolution to look at these very intriguing lamina. And you see also here in the geochemical patterns, now you're looking at calcium over strontium variability that is reminiscent to the sub-Milankovitch, this millennial scale variability we also know from the Uslan limestone. We still don't know whether it's correlatable, whether it is climate related at all, and whether it's similar climate processes influencing both localities. But I'm sure that Jakob will be able to come up with intriguing stories if we give him like a few months more time. He might give a next sedimentary lunch presentation with very cool results, but I wanted to show you already now the intriguing patterns that we observe on both sides of the Atlantic Ocean in the prelude of the lower Kalwasser effect. But I think now it's time to go back to cyclostratigraphy in itself, and then we move up the geological timescale a little bit. We go into the Femmenian. We're going to look at how Europe and the US can provide different sections that constrain the timing of the Femmenian timescale. And also here, we'll start with Germany. We'll start in the Sauerland. Here you look at a quarry, still active quarry, the Effenberg quarry, where you see a very, very nice limestone shale alternations. But if you look carefully, you also see here the annulata anoxic shales, and here this bed here, that's the Dasbeck shale. I remember correctly, 56 limestone shale alternations. And if you zoom in into these alternations, and if you measure the samples with portable XRF, you see very nice expression of those cycles in titanium over aluminium. So shales and limestones are characterized by a distinct signature in titanium and over aluminium. And that is important because both titanium and our aluminium are relatively immobile elements for post-depositional diagenesis. And at the same time, we interpret it as a proxy for the grain size of the silicic-elastic fraction, as a proxy for the intensity of riverine input with, and as you can see here, the shales have high titanium over aluminium, so therefore are suggesting high riverine input, and the limestones, of course, vice versa. The astronomical interpretation that Nina Wichern made, she is the PhD student that studied this, is that these 56 cycles, these individual cycles, are driven by obliquity. And that interpretation is again rooted in the biostratigraphic constraints that we have through Thomas Becker in Münster, but also onto the fact that here you see a complete absence of amplitude modulation, right? I told you that if these cycles would be precession, we would expect a very clear bundling, with the absence of precession cycles during eccentricity minima. Here we don't see that. All the cycles are more or less equally strongly, or are more or less equally strong, and therefore they point to a more likely obliquity origin compared to precession. And so those two arguments combined make that Nina thinks that these cycles are most likely obliquity, but this is a rather unexpected result. This was not what we expected, that obliquity was so dominant in the interval in the Fernmanian at the Effenberg quarry, in the interval between the Annulata and the Dasberg black shale. And that is because if you look at numerical climate simulations of precipitation in Southeast Euramerica at the time. So here you see a result from my PhD. This is the simulated wet season precipitation in Southeast America. And you see here on a three-dimensional plot with dimension 1 obliquity on the x-axis, precession on the y-axis, and precipitation intensity in millimeters per month here on the color scheme. And you see that basically along the x-axis, there is no variability. Along the obliquity axis, there's hardly any variability. A little bit wetter during obliquity maxima compared to obliquity minima, but nothing much. All the action is along the y-axis. So we expect precipitation to respond to precession. However, the geological record tells us that it was more likely responding to obliquity. So that was quite an unexpected result that we still don't explain fully, or that we still we don't have the feeling yet that we fully understand why that is at this point. So therefore, the question here, why was Effenberg so sensitive to obliquity? That remains an open question. We need to do more research and more thinking in order to answer that question, especially that because if you go higher up in the stratigraphy, so here, this is the Effenberg lithological log that you've seen, the Annulata black shale, the Dasberg black shale. If you want to go all the way to the Devonian Carboniferous boundary, we have to switch sections, and we switch sections here to Oberrödinghausen. Oberrödinghausen also has the Dasberg shale and has some conodonts that allow us to connect the two sections with one another, both lithostratigraphically and biostratigraphically. And so we can make a composite. And here on this picture, you see actually the Hangenberg black shale with on top of the Hangenberg black shale, the Hangenberg sandstone, and on top of that is the Devonian Carboniferous boundary. So Nina also sampled the Oberrödinghausen section, and there she found actually a more precession-dominated interval when she went higher up in the section. So the climate system switches back to precession apparently. But here I want to focus not on the paleoclimate so much. I want to focus on the stratigraphy. So here you see the composite record between Effenberg and Oberrödinghausen, and you see the astrochronozone counting done by Nina. She counts 14 astrochronozones in the composite record, with about 2.4 million years between the Annulata and the Dasberg shales, and 2.3 million years between the Dasberg shale and the Hangenberg shale. And so now the question is, how does this composite record from Germany compare to a time equivalent section from the United States? Well, in order to do that comparison, we can look at a paper published by Damien Pass et al. 2018, where in the Illinois basin, they find a total duration for the total Femmenian of 13.5 million years based on the counting of those 405,000 year cycles. So here you see the result of Pass et al. So you see also they count 405,000 year astrochronozones, and we were able to plug in through the Annulata event and the disappearance of a certain biostratigraphic marker here, we were able to connect our astrochronology to the astrochronology by Damien Pass here at the Annulata black shale, right? So that's here connecting to Femmenian cycle 22 by Damien Pass. And if you do that, actually the number of cycles in between the Annulata and the Dasberg black shale adds up as so 6 astrochronozones between Annulata and the Dasberg black shale. There is agreement on that between Europe and the US. Also 6 astrochronozones between the Dasberg and the Hagenberg black shale. Also agreement on that. What we do disagree about, not everything is settled. The Hagenberg crisis in Germany occurs near the end of cycle 34. That is exactly where, so at the top of cycle 34, that is where Damien Pass et al. Put the Devonian Carboniferous boundary, but you know from the German lithostratigraphy that on top of the Hagenberg black shale, there is the Hagenberg shale, the Hagenberg sandstone, and the Stockholm limestone. So the question is, do all of these lithostratigraphic units, do they all fit within the Femmenian astrochronozone 34? Or possibly do we need to add another astrochronozone number 35, in order to accommodate all that stratigraphy that still occurs in the latest Femmenian in Germany? So that is also a question that remains settled. But I hope that with this presentation, I was able to give you like a little bit of an update about the state of Devonian cyclostratigraphy. I hope that I was able to convince you that we now have some kind of a consensus between China, the US, and Europe that there are 3 astrochronozones for the Kellwasser crisis interval, with the lower Kellwasser in cycle 15. In cycle 16, that's the inter Kellwasser interval, and then the upper Kellwasser occurs in cycle 17. I hope that you are intrigued by these millimeter and centimeter rhythmites in the prelude of the lower Kellwasser. So they are sub-Milankovitch. They are no Milankovitch cycles. They're just too many cycles to be Milankovitch cycles in the Ussulen limestone or in the Angola formation in Europe. But they are intriguing, and the fact that these kind of rhythmites occur at the same time, both in Germany and the US, is very intriguing and calls for more research. And the Femmenian astrochronology, it has consensus on the number of astrochronozones in between the Annulata and the Dasberg black shale, as well as in between the Dasberg black shale and the Hagenberg black shale. However, there is more work needed before a true consensus can be made for the total Femmenian, right, as the issue I just explained with whether or not we need to add a cycle number 35, yes or no. And so with that, I'm at the end of my talk. I hope you found it interesting, and I'm open to answer all your questions, of course.